Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in the previous session, already we have discussed about engineering tribology subject. And also we have discussed on question bank and definition and terminology and theory part. So in this session, I want to discuss the question bank of where topic. So again, I will give the question bank introduction, and then I will explain briefly about where topic question. So the topic is wear and surface treatment. So already we have studied in theory part. Now in examination, so they will ask questions like this. They explain the term wear and elaborate different types of wears. So here first need to explain the wear term and then elaborate the different types of wears. So different types of wears, how many types of wears are there, and then need to explain briefly. So the wear refers to the gradual removal of or deformation of material at a solid surface due to mechanical action, so such as friction, cutting or sliding. So these are the three are mechanical actions. So in engineering tribology is a subject study of wear, friction and lubrication. So whenever two surfaces are in sliding motion, as two surfaces are contact each other, so there is a friction, there is a wear, and then you have to apply the lubrication to minimize the friction and to minimize the wear, and also to improve the performance of the product. So the wear is a removal of material during operations or some material deformation, solid surface to deformed due to the mechanical action. So it is common phenomena in mechanical systems and structures, so impacting the performance and lifespan of components. So wear can occur in various forms depending on the conditions and the materials involved. Here are the primary types of wear shown here. We'll explain. So different types of wears are there. So first one is abrasive wear. The abrasive wear description is this type occurs when hard particles or hard products force against, so that is protuberance force applied against and move along a solid surface, leading to material removal. So all these forces leads to the material removal. The types are two-body abrasion, that is abrasive particles are fixed, and three-body abrasion, the abrasive particles are loose. The case of loose, three-body abrasion, and two-body abrasions are abrasive particles are fixed. Examples: sandpapering, erosion of pump components by sand particles in water. Sand particles in water, these are the examples. So the adhesive wear is caused by the formation and breaking of adhesive junctions, cold welds between two sliding surfaces. So due to the adhesive pores. The formation and breaking will be occurred. These are called as cold welds, cold welding also. So the mechanism behind this adhesive wear is when two surfaces slide over each other, material transfers from one surface to another due to adhesion. The examples are galling, scupping, and printing. The corrosive wear description wear accelerated by the chemical or electrochemical reactions with the environment leading to material removal. So this one also the material removal process. So the removal process means the wear. The wear is nothing but that some material will be removed from the surface. So the corrosion wear falls under this category. They are accelerated by the chemical or electrochemical reaction with the environment. So it leads to material removal. The mechanism is oxidation or other chemical reactions weaken the material, which is then removed by mechanical action. The examples are rust formation on steel surfaces, degradation of metal surfaces in acidic environments. The corrosion wear, one is rust formation on steel surfaces. Whenever the components, the products are exposed to environmental conditions, so there is a wear, there is a rust that is called as corrosive wear. Due to this rust formation, some material will be removed. The degradation of metal surfaces in acidic environment. So whenever the chemical or chemical attack or acidic nature on the surface, the degradation will be occurred. Next, fatigue wear. So caused by repeated loading and unloading cycles, leading to the formation of cracks and subsequent material removal. So here, fatigue phenomena already you know. This is a mechanical property. Whenever the component is subjected to cyclic loads or repeated loads, the component will be fail after certain number of cycles due to the yield stress, the yield stress deformation. So it leads to the formation of cracks and also the subsequent material removal. This type of phenomenon is called as fatigue wear. So what is the mechanism behind this fatigue wear? Surface fatigue due to cyclic stresses results in fatigue, spalling or cracking. The examples are rolling contact fatigue in bearings and gear tooth fatigue. The repeated loads occurred in mechanical components like bearings and gear wheels and connecting rod and piston. The piston moves inside the cylinder top to bottom and bottom to top. A load acting on the piston. So that is the gas load. This one also one type of cyclic load. So bearings, two types. General bearing, that is sliding bearings, sliding contact bearings or rolling contact bearings. So the rolling contact fatigue in bearings and gear tooth fatigue. Next, erosive wear, the caused by the impact of solid or liquid particles against a surface. So the mechanism is particle hit the surface with high velocity causing material to be removed by cutting or deformation. So caused by the impact of solid or liquid particles. Whenever the component subjected to high force liquid particles or high impact load with high velocity, whenever the particles hit the surface, what will happen? The material to be removed by cutting or deformation. The examples are erosion of turbine blades, wherein pipelines transporting slurry, turbine blades. Frequently, the turbine blades subjected to high velocity particles. It may be solid or it may be liquid. Fretting wear. The fretting wear occurs due to small amplitude oscillatory motion between two contact surfaces. So the mechanism behind this fretting wear, the repetitive motion causes surface degradation and the formation of wear particles. The examples, the fretting in bolted joint, contact surfaces, in electrical connectors. So whenever the oscillatory motion between two contact surfaces are present, there this type of fretting wear will be occurred. So why? Because repetitive motion, the repetitive motion causes surface degradation, the to and fro motion. Cavitation wear. And description, this type of wear caused by the formation and collapse of vapor bubbles in a liquid near a solid surface. The cavitation will be occurred. So whenever the vapor bubbles are collapsed, so the mechanism is the implosion of vapor bubbles generates shock waves that remove material from the surface. The examples, damage to ship propellers, pump impellers, and hydraulic turbines. So these are the examples for this cavitation wear. Next question, explain briefly about surface fatigue wear and how it is controlled. So here in previous question, the types of wear he has asked. Now he has asked to explain briefly about surface fatigue. So what is this surface fatigue wear and then how it is controlled. So already we have studied in the previous question about fatigue wear. So see once again here, surface fatigue wear occurs due to a repeated cyclic stresses acting on the surface of a material, leading to the initiation and propagation of cracks. So whenever the component subjected to cyclic loads, it leads to initiation of cracks. So over time, these cracks grow and intersect, causing material fragments to detach from the surface. This type of wear is commonly seen in rolling contact situations, such as in bearings, gears, and cam follower systems. This type of wear is commonly seen in rolling contact situations. One is bearings, gears, and cam followers. So the mechanism behind this type of wear, initiation is micro cracks form on the surface due to cyclic loading, the micro cracks. Propagation, these cracks grow with continued stress cycles. The material removed, eventually the cracks intersect and lead to the detachment of material particles, resulting in pitting, spalling, or flaking of the surface. Examples: a fitting on gate teeth, spalling in ball and roller bearings, cracking in railroad tracks. So, the initiation micro cracks form on the surface due to the cyclic loads. So, the example for this surface fatigue wear, gate tooths and ball and roll bearings, cracks and railroad tracks. So, how to control this surface fatigue wear? The control of surface fatigue wear, one is material selection. The proper selection of material it gives the long life of the component. So that's why the selection of material is very important in designing. So use materials with high fatigue strength, toughness and hardness. They employ surface treatments like carburizing, nitriding or induction hardening to increase surface hardness and resistance to crack initiation. So before designing the component, you should select proper material for proper application. So the fatigue wear depends upon this the material fatigue strength and toughness and hardness. And also you can enhance the properties with the help of carburizing, nitriding or induction hardening. These are treatment, the surface treatment process. It gives good properties. Surface engineering. So apply coatings such as chrome, nickel or tungsten carbide to improve the surface hardness and reduce wear. So by applying the coatings, you can control the surface fatigue wear. Because the surface hardness will be improved. Use short peening or laser peening to introduce compressive residual stresses on the surface. Short peening or laser peening. So which helps to resist crack initiation and propagation. Next, third one is lubrication. Ensure proper lubrication to reduce friction and wear. So use lubricants with additives that form protective films, reducing direct metal to metal contact and distributing loads more evenly. So use proper lubricants with additives. So you can minimize the metal to metal contact. Wherever the metal to metal contact is possible, there is a friction and a wear. So always you should apply lubrication to separate the metal and metal contact. Whenever you use lubricant between these two sliding surfaces, they will be separated and you can minimize the metal to metal contact. So design improvements. Optimize component design to distribute loads more evenly and avoid stress concentrations. Use larger radii at the corners and fillets to reduce stress concentrations. So whenever the component having irregularity or sharp edges, there is a stress concentration. To avoid this stress concentration, always prefer the large radii corners. So example, suppose this is a uniform bar. So in this, the stress distribution is uniform whenever this component is subjected to tensile load. Suppose the irregular component is having like this. So in this, the stress distribution not in uniform. So there is a stress concentration at this sharp edge. To avoid this, use larger curvature like this with the radii. So you can minimize the stress concentration. We can't avoid completely. So that's why you can optimize the component design in initial stage. So you can minimize the surface fatigue wear by improving the new designs. The regular maintenance and inspection. Perform regular inspections to detect early signs of surface fatigue, such as micro cracks or fitting. Scheduled maintenance and replace worn components before significant damage occurs. So whenever you are doing the regular maintenance, there is no need to replace the component frequently. So the scheduled maintenance and replace the worn components. So before damage occurs, whenever you observe some small cracks or fitting, so immediately you need do some maintenance and conduct frequently inspections. By doing this, you can minimize the surface fatigue wear. Next, controlled operating conditions. Avoid excessive loads and speeds that can increase stress on the surface. They implement proper alignment and balance in rotating machinery to reduce uneven loading. By addressing these factors, surface fatigue wear can significantly reduce, leading to longer component life and more reliable mechanical systems. Though addressing these factors, surface fatigue wear can be significantly reduced, and also at the same time, it gives longer life. Next one is write short notes on fretting wear, surface fatigue wear, already we have seen, and erosion wear and percussion wear. So fretting wear occurs due to small amplitude oscillatory motion between two contact surfaces. This type of wear often arises in mechanical joints where there is a slight relative motion between the surfaces under load. The occurs due to the small amplitude oscillatory motions between two contact surfaces. So generally arises in mechanical joints, and also there is relative motion between the surfaces under load. Whenever these mechanical joints subjected to load, there will be a relative some motion. like example couplings, universal joints. Clear? The mechanism, the repetitive small movements cause surface degradation. This leads to the formation of wear particles and potential oxidation common in bolted joints, splined shafts, and electrical connectors. The prevention is use of lubricants to reduce friction. The application of surface coatings or treatments. The designing for better fit and reducing relative motion. These are the preventing methods. Next, surface fatigue wear. So, in previous question already you studied. This wear caused by repeated cyclic stresses on a material surface, leading to the initiation and the growth of cracks, which eventually result in material removal. The mechanism is micro cracks formed due to cyclic loading. Cracks propagate and intersect, causing material to fall or flake off, common in rolling elements like bearings and gears. The prevention is using materials with high fatigue strength, surface treatments like carburizing or nitriding, proper lubrication to reduce stress, regular maintenance and inspections are needed. Next, erosion wear. So, this erosion wear is the result of mechanical action where solid particles or liquid droplets impact a surface leading to material removal. So, the examples, the turbine blades and pump impellers always subjected to the liquid particles impacting. So the high velocity particles or droplets strike the surface, the causes cutting, deformation or material displacement. You can see in pump impellers and turbine blades, these are frequently subjected to this type of particles. It may be solid or liquid droplets. So due to this type of impacting leads to erosion wear. So erosion wear nothing but the material removal will be happen. How to prevent this type of erosion wear? Use of hardened material in place of softer material, and more erosion resistance material is required. So use very hard material. So more strength is required. So whenever the particles are impacting on this surface, they will not affect. So applying protective coatings. Apply some coatings on the surface. It gives life of the component and also minimize the wear. Designing components to minimize direct impact zone. So in designing stage, so some need to implement design improvements to minimize the direct impact zones. Controlling the velocity and concentration of erosive particles. The velocity also you can minimize the impacting velocity, and the concentration of erosive particles. Which particles are impacting on the surface, you can concentrate. So by using these methods, you can prevent this type of wear. Next, percussion wear. The percussion wear occurs due to repetitive impact are hammering actions on a material. So leading to deformation, material displacement, and eventual wear. The mechanism is repeated impact causes surface deformation. The material may crack and fall off due to the constant hammering. The common in tools like hammers and anvils and in machinery subject to repetitive striking actions. Next, how to prevent? Using tough or impact resistant materials. So having the material high toughness and high strength to withstand the impacting. Applying surface hardening treatments like nitriding, carburizing, annealing. So these all are surface hardening treatments. So apply these treatments. By using these hardening treatments, you can improve the life of the component, and also you can minimize the wear. Properly designing components to distribute impact forces evenly. So already we have seen in previous question. So minimize the stress concentration. So wherever sharp corners are present, so use large radius to minimize the stress concentration. So proper designing of the component gives good life and reliability. Regular maintenance to identify and mitigate early signs of wear. These brief notes highlight the key aspects of each type of wear and common strategies for their prevention and control. Next one is describe briefly between Harthart's theory of adhesive wear. So in theory part, already we have studied about this adhesive wear. So this is a recognized model that describes adhesive wear where occurs due to the formation and breaking of adhesive junctions between the two sliding surface is given a brief description. Adhesive junctions, when two surfaces come into contact, asperities, microscopic high points on each surface interact and may form adhesive bonds. So during relative motion and adhesive bonds can shear, causing material transfer or wear particles to be generated. So wear volume. So here given equation V is equal to KLD by H. Here V is the volume of material and load L and sliding distance D and hardness of softer material H. So dimensionless coefficient K. So key components of wear coefficient and applied load. The sliding distance D and hardness H. It leads to the low wear rates as harder material are more resistant to deformation and adhesion. So some assumptions are made. So that is the wear debris are formed mainly due to the adhesive forces between the contact surface. So the application of theory is used to predict wear in various mechanical systems such as bearings, gears and sliding contacts. It helps in selecting material, designing components to minimize wear and extended service life. So limitations are there such as lubrication and surface roughness and temperature. These are the say real world conditions. It is primarily applicable to metal on metal contact and may not accurately predict wear in non-metallic or composite materials. So by using this theory, engineers can estimate wear rates and design systems to reduce adhesive wear and improving the reliability and longevity of mechanical components. So these are the references I have taken for this revision of question bank. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.